All right. Good morning, everyone. Anton here, your presenter for today, and as always, before we begin, just a few basic items to remember. As you know, we do not take questions directly from the audience during the webinar. If you have any questions, we do have a dedicated team standing by to answer them. So just type them in the text window in Zoom, and somebody will get back to you either during the presentation most of the time, or if your question requires more careful consideration, then somebody will get back to you afterwards. Also, if you require, would like to receive, excuse me, a certificate of attendance for this event, also please contact whoever invited you to this webinar, and or directly to GlobeCore, and you can get a certificate of attendance for this one. Okay. So with this out of the way, I'm glad to be here with you today to present this topic. Today we're going to talk about, well, the title of the show today is Innovative Auxiliary Equipment for Transformer Manufacturing. And perhaps this is a bit of a misnomer, but what I mean is that a lot of the equipment and processes that I'm going to talk about today has to do a lot with transformer maintenance as well, not only in manufacturing, but of course, these things are also important for manufacturers of transformers. And I guess we can go to the next slide. Right. So in our past webinars, and we've had a few already, so we already discussed insulation as one of the most vulnerable parts of a transformer. And in fact, a transformer lifetime is defined by the lifetime of its paper insulation. And in its own turn, paper insulation is impacted by water a lot because water causes destruction of cellulose molecules and promotes reduction of dielectric strength. And so it's very important to remove water from transformer as much as possible and perform this procedure periodically during its entire lifetime. Next slide, please. So before we go into detail, let's quickly recap the three main sources of water in the transformer. So first of all, it's the water, residual water, you may call it, in the solid insulation that has not been removed during the production process at the factory. And manufacturers sometimes, or in many cases, do not possess the necessary infrastructure or equipment to ensure the required level of humidity or the required dryness of new transformers. And another common misconception is the assumption that new oil is dry. So new oil is not necessarily dry. It could have accumulated moisture already. And so transformer companies might actually inadvertently introduce significant amounts of moisture into their new equipment. The second source, probably the most common one, is the atmospheric water from the air. So every time we have a problem with the tightness of the transformer, there is a leak of some sort, water from the atmosphere comes in. And this is because transformers heat and cool down periodically. So when the temperature increases and when it drops due to thermal expansion and contraction, what happens is that a process that really resembles breathing. So transformer intakes atmospheric air and obviously takes in water from that air. And this water from the atmosphere goes into the transformer and it becomes part of the oil or the paper. And this obviously is something we really don't want to happen. The third source of moisture in the transformer is intrinsic. It's internal, basically. When cellulose and oil age, when they oxidize and their molecules break down due to all those chemical processes, all these chemical reactions, or most of them, emit water or form water. So especially if the temperature is high or if the insulation system is significantly worn, this will be another source of moisture in the transformer. Okay, next slide, please. So one of the most important things for transformer is obviously the water content in the system, because water is a slow poison, and slowly but surely it kills the transformer. And here we have a graph that shows a dependency which was worked out by Lars Langard et al. And they have been presented in a separate article. And these dependencies show the impact of temperature and water content on the life cycle of transformer solid insulation. As you can see from this graph, a change in a percentage of water in paper has a very significant effect on the transformer lifetime. You can see that if the transformer has a humidity of 1%, its lifetime expectancy is about 30 years. If it's operated at a temperature around 80 degrees Celsius. But if the transformer works at the same 80 degrees Celsius, but with humidity in the paper of about 3%, and its life expectancy is just 6 years. And so using this data, we can obviously see the necessity of continuous monitoring and control of moisture in our equipment to prevent any increase that may happen due to internal or external processes and influences in the transformer. And increase of moisture has quite a bit of negative effects for transformers, such as the reduction of dielectric strength of the oil, increased degradation of paper, oil aging, and a reduction of the oil's performance. And basically, all of these are bad for the transformer. Next slide, please. So in general case, it's safe to assume that about 99% of water in the transformer is contained in its paper. However, water is never stationary and never static in the transformer. It's in a state of constant flux. When the temperature increases, the water migrates from paper into oil. When the temperature is reduced, the process is reversed and water goes back into the paper. But it's also important to keep in mind that the water deep inside the paper, in the layers of paper, largely remains unaffected. So this is another thing to consider. Next slide, please. So as we mentioned, the duration of transformer life is directly related to paper. So let's look at the paper in a bit more detail. So the transformer paper is responsible for both physical, to serve as a physical barrier and an electrical barrier, like an insulator. If the paper becomes weakened physically, this basically causes irreparable wear of the transformer and reduction of the electric strength, which causes arcing, and internal discharges, and all those discharges will cause formation of volatile and flammable gases, which will obviously cause a significant catastrophic events in the transformer. So insulation paper must be must be resistant to thermal effects, resistance to heating, but it should also have the ability to conduct heat. And we know that paper is quite sensitive to temperature, so increased temperature in a transformer is actually enemy number 2, only followed by water in the transformer. So increased temperature in the transformer causes accelerated aging, and the performance of the paper, the characteristics, the condition of the paper in the transformer cannot be restored. Once it's damaged, it's done. It cannot be restored. So once it loses its performance, the paper loses its quality, and obviously we now face a significant reduction of life expectancy for the transformer. So let's go to the next slide. So to estimate the condition of paper insulation, there is a number that is used. It's called the degree of polymerization, or polymerization degree. And in this slide, there is a table that gives you a connection between polymerization and the mechanical strength of paper. And we can see that new paper can withstand a load of up to 170,000 kPa. If the paper is aged, basically it only can withstand about 3,100 kPa. So new paper usually has a polymerization degree of 1,200 or 1,250 or so. And as the paper ages, the cellulose molecules break down and the polymerization drops. Normally, with normal aging, the polymerization degree is around 600 to 800. But as it falls down to 200 or less, that means the paper is basically unusable and unserviceable. and this is actually stated specifically in the standards by IEEE. We have hello again. I'm sorry, just had an internet outage. This is unfortunately something outside of my control entirely. So let me just reset myself here a little bit, just a minute. I apologize sincerely for this interruption. I'll be back with you in just a second. Okay, so I'm not quite sure what was the last thing that you heard from me, but let me start from this. Okay. Oh, thank you, Diego. So anyway, 200 degree of polymerization is basically the end of transformer paper. When it falls down to, yeah, thank you, gentlemen. Well, anyway, as the degree of polymerization drops to 200, that's it. That's about it. This is the time that you cannot use the transformer again. And basically, this 200 is set in stone. It's in the IEEE standard. So, well, what we can do is we can do Furan analysis that allows us to determine the degree of the polymerization, the length of the cellulose chain, the link, and the degree of polymerization. And this is a good indication of the condition of the transformer and for how long it can be operated. All right, let's go to the next slide now. Great. So in this slide, what we can see is the impact of water on the oil's dielectric strength. On the x-axis, we have the relative humidity. On the y-axis, we have the relative dielectric strength or breakdown voltage. So we can see that the breakdown voltage or dielectric strength of humid oil is relatively low, but has a slight tendency to increase. However, when we add a certain amount of water, the dielectric strength drops down significantly and drops to about 30%. And low BDV means that the insulation system cannot prevent electric arcs. And this means that electric arcs happen inside the transformer, generate a lot of gas and decomposition compounds, which will have a negative impact on the transformer and will reduce the transformer life cycle. And this graph comes from the Vaisala company. They did it by continuous monitoring of 8 different cases and then building this this graph based on their online monitoring systems. Okay. Right. Next slide, please. In here, we have a collation of methods that are used for drying of solid insulation transformers and their comparison in terms of their capabilities for being used for different size transformers and service conditions, such as repair shops or on-site repairs. If you see a plus, that means that it's possible to use this particular process for this specific task. Minus obviously means the opposite. Okay, so for convenience sake, we've classified transformers into large transformers, with power ranging from 100 to 250 MVA, with voltage of at least 220 kilovolts. Also, medium-sized transformers from 40 to 250 MVA and voltage of about 275 kilovolts, and small transformers from 5 to 40 MVA with a voltage of 145 kilovolts. So also, this slide does not present all of the available methods of drying, but only those that we believe, from our experience, that are the most practical and most common for oil field transformers. And we can go to the next slide now. So for the first method, what we're going to talk about is a drying of transformer with the sorbent. And this method, on the one hand, can be called a preventive method because it reduces or maintains a certain humidity level in solid insulation during the transformer operation. On the other hand, this method can also be classified as indirect drying method because its effects on the solid insulation are facilitated by its effects on the oil. So in a way, it's indirectly impacts the solid insulation. So what happens is several columns filled with an absorber are connected to a transformer, and those sorbents usually have very high ability to capture water. And then the oil circulates slowly through these cartridges at a low rate, which usually does not exceed something like 30 liters an hour. And at the same time, the sorbent basically extracts water from the oil. And since in a loaded transformer, water constantly migrates from liquid into the solid insulation and then back again. If you have this continuous drying cycle in oil circulation, it also dries the solid insulation because obviously as you extract water from the oil, the balance shifts, and so more water is released from paper into the oil. So there is a practical case that we've had in America, in South America, I believe, using GlobeCore made absorbers for 8 months. What we got was a absolute content of water in the oil reduced from 25 to 14 ppm, and relative humidity basically of oil was reduced from 16.9 to 9.3%. at the average transformer running temperature. And what is perhaps the most important is that the humidity of solid insulation dropped from 1.3 to 0.7%. So back to the graph, which demonstrates the impacts of temperature and water on transformer solid insulation. Using interpolation for these graphs shows that, for example, for a temperature of 80 Celsius, the reduction of moisture content in solid insulation from 1.3 to 0.7% actually improves the service life expectancy of such insulation by approximately 25 years, if you can believe. Okay. Next slide, please. So one of the perhaps simplest methods of drying solid insulation is hot air purging. What it does is basically blowing hot air at a temperature of 100 to 110 degrees Celsius through the transformer. However, the method has some limitations and drawbacks. One of them is the high probability of overheating the solid insulation locally or entirely. Also, this method only works if you pump all the oil from the transformer. And since there is a significant degree rather of heat loss through the transformer tank, this process is actually quite expensive in terms of electricity or energy. It's not very energy efficient. So to reduce the heat loss when you do this dry air processing of the transformer, it's probably advisable to insulate the transformer tank from the outside to reduce the heat loss. And also, since the tank is actually quite large, if you input air into the tank at a temperature about 100 degrees Celsius, you might have overheating there. But on the other side, the temperature will not be enough, so there will be some uneven heating. And all of this makes hot air drying less than perfect and less than most efficient. And it's usually only used when there is no other alternative. Anyway, hot air drying is most commonly used for smaller transformers with tanks that are not designed to withstand high vacuum. And this is usually done in repair shops. Let's go to the next slide. Next slide, please. Right, so in manufacturing facilities and in repair shops, sometimes what people use are special chambers or ovens, which dry the system not only by heating, but also by vacuum. So the core of the transformer is extracted from the transformer tank. It's installed into this oven, and then it's subjected to heating, which causes water from the insulation to evaporate. And when a certain temperature is achieved, then the vacuum pump kicks in and starts creating vacuum in the chamber to evacuate the water vapor and increase the drying efficiency. And as you can see on this graph on the left of the slide, this is, I'm sure, something everybody knows, that vacuum reduces significantly the boiling point of water. As we can see, that we can safely extract water from paper under vacuum with temperature not exceeding 65 degrees Celsius. And this is good for the paper because it does not have the detrimental effects. It does not decompose the paper. One limitation, perhaps, of this method is the need to open the transformer and extract its core, which only then can be installed in the chamber of this oven. And this is not something you can do in the field. So the transformer has to be transported to the shop. It has to be maintained and serviced at the shop where the chamber is located. However, if you have a chamber of significant size or adequate size, you can use it to dry a transformer of just about any size. In general case, at any rate, such drying in vacuum chambers does require quite a bit of energy, which is expended to heat the solid insulation inside the oven. And basically, this process is also quite energy efficient. Energy intensive. It requires a lot of energy. Next slide, please. Next slide, please. All right. So the next method is a vapor phase drying. this is also done under vacuum, but the heating is not done by air. Here, the heat is carried instead of air. It's carried by volatile solvent with a high flash point. And this vapor is heated by electrical heaters, and it passes over the core of the transformer, heating the insulation. And then what solvent condenses on the surfaces, it's collected and sent back to the evaporator for consecutive heating. Right. So after several cycles, the temperature of solid insulation increases and increases, and water evaporates from the internal layers of the insulation as vapor. And compared to regular drying by hot air, where temperature cannot go up higher above about 110 degrees Celsius, solvent vapors can actually be heated to approximately 130 Celsius without the risk of insulation aging. And this makes the heating process quite a bit faster. It takes about half the time that required for the hot air drying. So this method is good for all sizes of transformers, but once again, it's mostly usable if you have a repair shop with all this equipment. The biggest limitation is that when you use a solvent, those solvents are flammable, and there is a risk, obviously, that at a certain concentration of vapor and air, the mixture becomes explosive. So this equipment can be quite expensive because it needs to be intrinsically safe. So there is a certain risk associated with this process and certain costs. All right, next slide, please. Next one we're going to look at is circulation of hot air and spraying of hot air in vacuum. This is used both in repair shops and in the field to dry transformers of small, medium, and large size. To perform this process, you'd need like an oil processing rig, an oil processing machine that includes a heater and a powerful vacuum system. And you also need special nozzles for spraying the oil. So the oil purification system is connected to the transformer. It creates a closed circuit through which the oil circulates continuously. So hot oil circulates through the transformer in parallel for more even heating of the windings. And also it's sprayed over the windings through the nozzles. So when a certain temperature is reached, the oil is drained and vacuum is applied to the transformer tank. So in one such cycle, the insulation is heated, moisture evaporates, water vapor is reduced from the tank by vacuum pumps. And these cycles are repeated until we achieve the required low moisture content, in solid insulation. This method is quite versatile, and according to our classification, it works for just about any type of oil-filled transformer and for any type of service or repair shop. Again, this technology does require quite a bit of electric energy because you need to supply hot oil into the transformer at a temperature of about 100 Celsius. And another complication is that you need to install the nozzles inside the tank. Okay. Some of the other limitations here is the relatively low efficiency because, again, we have heat losses through the transformer, through the walls of the transformer tank. And it's also possible to overheat the oil inside the heater. And as we know, the high temperature breaks the oil molecules. And the problem here is that usually, you have the oil processing machine connected to the transformer by hoses, and to receive to get the necessary temperature in the transformer, due to heat losses in the hoses, the temperature of the oil in the heater should be around 140 degrees Celsius, and that is not very good for the oil. You can damage the oil doing that. And of course, since we use vacuum in this in these cycles, the transformer tank must be strong enough to withstand that vacuum. Next slide, please. All right, cold vacuum. Another clever process. This is also done. This also involves heating of transformer and a vacuum. The important condition here is that the temperature of insulation must not fall below 20 degrees Celsius. So This method is implemented using a special cold trap that is designed to freeze out the water vapor. And this really increases the efficiency of vacuum pumps, and it allows to extract the vapor of water from the transformer tank quite quickly. The cold vacuum method can be used for usually for small and medium-sized transformer, and can be used on site. The limitations here again is because we use vacuum. The transformer tank must be strong enough, and also the process is long. So to efficiently remove water using a cold trap, we also need to heat the insulation periodically, and these cycles take quite a bit. And to dry a transformer in this manner, you might need actually several weeks. Okay. Next slide, please. So to summarize the things we've talked about, all of these methods are usable in practice. However, none of them is completely universal, or cannot, none of them is an all-for-one solution. Some are limited by size, some are limited by the location, because some cannot be used in the field. So one good method that we think is good for preventive reduction of moisture in the transformer when the transformer is running and it's operating is the continuous drying using a sorbent. However, if it's not possible to use this method for some reason, then the most important thing that needs to be considered in the first place is whether the transformer tank can hold a vacuum of 0.1 millibar or less. So to dry insulation in transformer with tanks that can hold this vacuum, you can use just about any method from the table in that slide that we've shown with the table of methods, which does not require extraction of the core, regardless, depending on where the drying is performed, whether it's done in a shop or on site. And this is especially important for medium and large transformer, and because it may be difficult to extract the core from their tanks. For small transformers that cannot hold this vacuum, perhaps hot air drying is satisfactory. If a medium or large transformer tank cannot hold the vacuum, it's still necessary to extract and dry the core in a vacuum oven, although it might be technically difficult. So some of the other limitations of the methods that we've discussed is they usually take a long time. Depending on the method, depending on the size of the transformer, it can take weeks or months. All of these methods that I mentioned require quite a bit of electricity to run, and some of them, or rather most of them, are quite expensive. Okay, so this, however, can be addressed by using another very promising method, the low-frequency heating. And we're going to demonstrate equipment for this today. So next slide, please. So low frequency heating is a very promising approach to drying of transformer solid insulation. First, it was used in mid-1980s when drying distribution transformers. The idea is to apply a low frequency current with a frequency of maybe 0.4 to 2 hertz, a low voltage current to high voltage windings, and to shorten the low voltage windings as well. So during this process, high voltage and low voltage windings of the transformer are actually evenly heated to a typical temperature of 110 to 120 Celsius. So the low frequency heating device is fully automated. It works automatically. It's controlled by PLC under SCADA control. First, before the process begins, the operator inputs all of the data for the transformer, and then the temperature of the windings is controlled periodically to prevent overheating of insulation. And the measurements are taken by a special electronic sensor. And also there are additional sensors that are installed into the transformer tank for redundancy. So we have an absolutely precise measurement of the temperature. So when these diagnostic tests are complete, the heating process proper begins automatically and follows an automatic algorithm, automatic cycle. And The quality of insulation when using this method is increased significantly if we compare it to more traditional systems that use, for example, vacuum drying or hot air. And this is due to the fact that in this process, in the low frequency heating process, the source of the heat is actually the winding itself, which is the ideal place of application of heat to extract water from insulation. And the duration of the drying process is reduced quite significantly compared to regular systems which use hot air and vacuum. And in its turn, it allows us to save up to 50% of energy. And in terms of real numbers, if we're talking about a relatively small power transformer, that would mean about 2,000 kilowatt hour. So when we use traditional methods of drying with circulating hot oil and with vacuum for large transformer, the average water extraction rate is about 2.5 liters per day. But when we have nozzle spraying of hot oil with low frequency heating, we get an extraction rate of up to 20 liters per day. And it's important to have a continuous monitoring of temperatures at the same time of high voltage and low voltage winding to prevent breakdown of oil because breakdown voltage is reduced in vacuum. And it's also important to have a qualified operator running the system. For medium and large size transformers, the LFH method, low frequency heating method, is used in combination with one or actually several other methods, such as evacuation, circulation of hot air, circulation of hot oil with spraying, etc. So it is the flexibility, efficiency, and versatility of the low frequency heating method that make it today probably the most promising method for drying of solid insulation in transformers. Next slide, please. And I believe we have our engineer standing by in our shop, in our production shop, but this is here in this slide. You can see the equipment that will be demonstrated. It's a comprehensive solution that allows a very efficient drying of transformers in the shop or in the field. Next slide, please. Right. So for this equipment, before we go to our shop and see the equipment, a few words about it. There are several components that are used with, as a complex with this equipment. One is the TEAMS system. TEAMS stands for Transformer Installation Management System or Monitoring System. There is the special Globe Core LFD device, low frequency dryer. There is a thermovacuum system for transformer, or it can be a CMM or UVM. For those of you who are familiar with our product range, you'll know that CVM is lower vacuum, UVM is higher vacuum. And it depends, the selection depends on the amount of oil in the transformer. And also all of these machines have different processing rates that can vary from 400 to 15,000 liters per hour. It can also be used in combination with a vacuum oven, with the hot air blower, with a cold trap, and of course with an oil regeneration plant. So in the next few slides, we're going to look at some of the more typical combinations of equipment from for drying of insulation. If we can go to the next slide. Thank you. So the first combination we're going to look at is a combination of LFD plus a UVS. UVS is the vacuum oven that you put the transformer core into. So before the process begins, the core of the transformer is placed into the oven, and then the LFD heater is connected to the transformer winding. In the process, moisture goes from paper insulation into the chamber of the oven, and then a vacuum system removes that moisture from the oven. The heating process and the evacuation process are completely automated. The duration of heating, the holding time under vacuum, and the number of cycles are all set by the operator according to the process requirements. So in the drying process, there's also the simultaneous process of heating the windings, extraction of water from solid insulation and extraction of water, evaporated water from the vacuum chamber. Next slide, please. We can also combine the LFD with the UVM or CMM oil processing system. And the system here works as, like this. So we heat the windings with an LFD. The moisture from the solid insulation migrates into the oil inside the transformer. And then the thermal vacuum drying and filtration system, like a CMM or UVM, reduces that water content, removes that water from transformer oil, and it also degasses and filters the oil. And this cycle can be run again and again until the moisture content in the oil drops to 10 ppm or below. And when this usually happens when the windings are heated to about 75 degrees Celsius. Next slide, please. Next slide, please. All right, here you can see a combination of LFD with what we call a Mojave heat. Mojave is a very famous desert in the United States, very dry place. And, you know, not a coincidence, this name. So this is a hot, dry air blower. Before the process begins, we drain all oil from the transformer tank. The LFD heats the transformer windings, and then we connect the Mojave heat system. We heat the windings with LFD, moisture evaporates into the transformer tank, and then the Mojave heat supplies very dry air into the transformer tank with a dew point of -50 degrees Celsius. The air is hot, and so when it passes through the transformer, it's so dry that it basically carries out all the moisture that has been evaporated from the insulation, and that air is pushed outside. Next slide, please. All right, here we have a cold vacuum combined with an LFD system. So first off, the windings are heated by the LFD. Moisture evaporates into the transformer tank. And then basically what happens is that moisture is captured by the cold trap. It freezes into in the cold trap, which has a temperature of -70 Celsius. And it's quite an efficient process now, because it allows to control the amount of moisture that the amount of moisture that is extracted from the solid insulation. However, this method requires that the transformer tank can withstand vacuum. If it cannot, then it's possible to use a special airtight bag, which is into which the core is placed for this process. Right, next slide, please. Okay, here we got a winning combination of an LFD, a CMMR regeneration system, and a UVM vacuum oil dryer. Of course, here we also heat the windings, then water goes from the windings from the insulation into the oil, and then we pass that oil through the thermovacuum system like the UVM, removing water from the oil and filtering it. However, the regeneration plant that you can see here, the CMM6RL in this case, what it does, it improves the chemical composition of the oil. It clarifies the oil and restores it, basically. It reduces the acid number, removes all the products of oil degradation, and it pretty much restores the oil to as good as new condition. Okay, so I believe next we have our connection from Timofey, the engineer.
Hello, I am Tim. Here we are at the GoPort store, and I'm gonna show you the equipment complexes mentioned above, right here, as they are in real. So here we have a testing transformer and low frequency heating device. As you can see, they are connected. This is a step down transformer. So we have power supply to the high voltage side. Secondary winding is short circuited, and A few words about this system. It enables to apply heat directly to the place where it is needed. So by heating the wirings, we heat solid insulation, and it helps to extract water from it very effectively. So operator can set the time of the process and the parameters of transformer. As the parameters are set, the heating process starts, and when the temperature is reached, it is maintained, and in cycles, the resistance of the wiring is measured, and coming from this, the temperature of wiring is obtained. So we control the temperature of the wiring, and to remove water from the transformer as a whole, we use the drying unit. This is the simplest unit in the GlobeCore product line. It has the capacity of 400 liters per hour. And with this unit, we treated this transformer. Low frequency heating device worked with no interruption, and we removed water in the daytime with the drying unit. It was very convenient to have the moisture sensor in the line connecting the transformer outlet and the inlet of the unit. In this line, we assembled the moisture sensor, and we observed the clear drying dynamics. So, as I said, we run low frequency heating with no interruption, and it enabled us to check the moisture content at the end of the day when we stopped the drying process, and to see its change in the morning when water was extracted during the low frequency heating operation, the night time. So what we have seen, let's say at the end of the day, we had something like 10 to 20 ppms moisture, and the next morning we observed values like 100 to 120 ppm. So in our estimation, using of this complex, I mean low frequency heating and drying unit, took something like 50% less time, and consequently 30 to 40% power consumption economy. So this was the first complex I wanted to talk about. Instead of this simplest drying unit, you can use more powerful machine, which has the capacity of 4,000 liters per hour. As you can see, it has more powerful vacuum system. It includes booster, root pump, and rotary wave pump. So with this equipment, the process will take less time. And again, talking about the service of transformer, the highly demanded ISHA is the regeneration technology. That's why the GlobeCore product line includes the whole range of regeneration units, particularly this one. Again, is one of the simplest regeneration units. It has capacity of 200 liters per hour and can be successfully used in the complex with low frequency heating, drying unit. Even this one is enough. Drying unit and regeneration. And talking about the regeneration, we mean not only treatment the oil, but treatment that transformer as a whole, because we regenerate oil in cycles, which helps us to extract chemically aggressive components, not only from the oil, but from the isolation and from the sludge. So this technology affects not only the oil, but the transformer as a whole, and enables to extend the lifetime of transformer. So this is what we have here at the moment. Of course, we also producing cold traps and Mojave heat units, but at the moment they are at the production. Probably we can see it somehow, but for now, that's all. So thank you. Please, questions.
Thank you, team. That was great. Good show. I hope everyone enjoyed and saw something interesting. We shall, however, continue now that you've seen the equipment firsthand. So a few words about that I would like to say about a different type of equipment, perhaps. I'd like to talk a little bit about diagnostics of transformer installation that can actually be combined with the process of continuous insulation drying. This is a solution that may be especially interesting for facilities that perform post-warranty and post-sale service to transformer. And all of these functions are combined in a system that we call TOR5, TOR5. One big advantage of the TOR5 is its simplicity. Basically, it consists of 3 sections enclosed in one case. There is the oil processing section for removal of moisture from the transformer oil. It has 3 adsorbent cartridges and a pumping system for the oil. So when the parameters of the oil reach certain limits that are preset by the operator, the TOR5 automatically switches from the diagnostics or monitoring mode into the filtration and drying mode for the oil. So as the water, as I've said several times, as the water in the transformer migrates from vapor into oil and back, such circulation through absorbers allows us to remove water not only from the oil, but also from insulation, slowly and over time. So using a TOR5 system on a transformer over the entire lifetime of the transformer makes sure the transformer is basically always kept dry. The next section that we got here is a monitoring and data collection system, the TIMS, Transformer Installation Management System. It is a combination of software and hardware that allows to control and analyze quality parameters of transformer oil that may be taken from either the transformer or maybe an oil purification system. It involves several sensors, a module that processes and transfers data, and software which also is protected by password for security. The next component is the TSS system, a transformer safety system, and that thing is designed to be connected to the transformer tank and to protect the transformer first by removing any air from the hoses and pipelines, and also to control the level of oil in the transformer during processing. So, for example, if there is a leak, the system is automatically shut down and all the valves are closed to protect the transformer against such leaks. One important factor of interaction of the system is that based on the results of continuous oil monitoring, when the oil is aging or when the dehydration process is not sufficient. It's also possible to see that it's time maybe to use a degassing or dehydration system, or even a regeneration system, maybe to bring it in, connect it to the transformer, and process the oil. So if you have these monitoring information, and if you perform the oil processing in a timely manner, degassing or regeneration, that obviously is always good for the condition of your transformer. So this TOR5 system can be combined, for example, with the UVM, which is probably the most versatile system and the most versatile method for this. And you can also combine this with the low frequency heating as well to help extract water from solid insulation into the transformer oil, and then to extract it from the transformer oil, as I've already described. Okay, next slide, please. All right, so the system has quite a few sensors. It has a router for connection and special software designed by Globcore. This system is installed directly on the transformer to be monitored, and it continuously collects data from those sensors. And using that data, the system calculates quality indices that allow us to see the actual quality of the oil and its moisture content. It can also give us an indication of the amount of water in the solid insulation. The TOR5 sensors take readings once every minute, 24 hours, 7 days a week, and they take the following parameters. So it takes temperature of the oil at 2 temperature measurement points. Also takes water activity in oil from the transformer. This is recalculated into relative humidity. This is also done at 2 measurement points. And it also takes the amount of hydrogen in the oil. So the measurements are transmitted via internet to a cloud server. And in that server, some math happens. There are some formulas that are used to calculate other parameters that will give us a much more complete picture of the transformer condition. And these include the amount of water in the oil in the transformer, the amount of water in the solid insulation, and it also gives us the calculated estimated dielectric strength of the oil as dependent on the solubility of water in the oil. 100% dielectric strength corresponds to a relative humidity of less than 20%. If the relative humidity goes up to 60%, then the dielectric strength drops down to about 30%. Another parameter that we calculate here is the oil quality index, and this may be something new for you, and more on that in just a minute. But all of the results are displayed on a web page, which is also password protected for additional security. The system's also all encrypted, so no third party will ever get access to your information. The information can be stored for years over the entire lifetime of the transformer, can be accessed at any time. If an internet outage occurs, like what we had today earlier, then when the connection is restored, the information still stored in the router is transmitted as a batch into the cloud server, and the process is resumed. So the number of parameters, the amount of information that we have access to through the TOR5, is actually more than the number of sensors we got. And this is done by using some clever calculation algorithms. A lot of the parameters allow us to go outside the limits of simply estimating water in transformer, humidity in transformer, and go to estimation of risks that are related or connected to the amount of water in the oil or in the solid insulation. So as I've said, the oil quality index, it is an indication that gives a relative number, a condition of the oil. It goes from 0 to 100%. If you have 100%, that means your oil is great, ideal condition. 0 means bad, old, aged oil. The oil quality index is a very good indicator of insulation oil degradation. It correlates very well with late acidity in the life cycle of the oil, and it also correlates well with interfacial tension. So calculation of the oil quality index allows us to, we don't have to measure those parameters, the acidity and the interfacial tension, and we will just know how old the oil is just based on the oil quality index. Additionally, as an indicator of possible faults or problems with the transformer, we have a highly precise hydrogen sensor in the system. And as you may know, hydrogen is basically one of the first gases to form in the transformer in case of a problem. It forms at about 150 Celsius, and it constitutes up to 59% of all the gases that are emitted when oil molecules break. So the content of this gas in insulation oil is a very informative parameter for diagnosing possible problems in the transformer, especially for partial discharges. So when you have partial discharges, the weakest hydrocarbon links in the molecules break down and release that hydrogen that we can later measure. Next slide, please. Right, so this system is great, and let's summarize why it's great. What it does is, using the TOR5 system, extends the transformer lifetime by dozens of years. For older transformers, the TOR5 gives us an indication of just how old the oil in the transformer is, and it gives us a good indication when we need to start repairing the transformer, or in the worst case, when we need to shut it down and decommission it before we have a catastrophic event in the transformer. Another good thing about it is that it increases, obviously, the service intervals for the transformer by preventively processing transformer oil. It also allows us to save money on laboratory analysis that we would usually do for a good picture of the oil, but this system is advanced enough to give us enough information about the oil to make informed decisions about the transformer. Also, transformer insurance can go down. The probability of transformer failure, if it's equipped with a TOR5, is significantly lower than for transformers that don't have that system. And this usually translates into cheaper insurance policies. Another thing is the reduction of the labor costs of the qualified personnel that you need to involve in transformer maintenance, such as people that take oil samples, or laboratory personnel, filtration equipment operators, and etc. So you would usually save on labor as well. One other important, last but not least, parameter is, or factor rather, is the environmental protection. When a transformer fails, if there is a leak or a fire or maybe an explosion even, that is usually an environmental disaster, even if a local one. So the TOR5 allows you to prevent such situations and eliminate any probability of environmental pollution that usually happens when transformers fail. So basically, if we add if we add the TOR5 system to let's go to the next slide. All right, can you guys hear me? I hope you can. Oksana, please write me if you can hear me. I think my internet connection just restored itself. All right, I think you can. Thanks. Great. Anyway, we need to go to the next slide before we continue. Okay, we got that. So, all right. This last one here is a quick summary of the efficiency of the equipment for comprehensive transformer servicing. The equipment that we've presented today are quite versatile, and it's very easy to select the stuff that you need to solve your specific tasks with such a wide range of products. The low frequency heating method reduces your electricity costs, power costs, and it also reduces the time required for solid insulation drying. The low frequency heating reduces the risk of overheating due to the technical solutions and the process technology. The equipment that we suggested today allows good moisture control and oil quality control. The Torr 5 does that for you. And also it's all automated, so you don't have the human error. You don't need to worry about someone making a mistake in the process of transformer servicing. So basically all of this translates into significant extension of transformer service life, which is ultimately our goal here, okay? And with this, I'd like to conclude this presentation today, and thank you all for coming, for visiting. It was an honor, as always, speaking for you. Again, if you have any questions, your questions will be answered later on if we haven't done so yet. If you need the certificate, contact your manager at Globecor. Also, if you need a recording of the webinar, you can have that from your manager. And once again, it was an honor presenting this to you. Thank you very much, and enjoy the rest of the week and your weekend. And I'll see you again very soon. Thank you.